Hello, everyone. Today, I'm gonna present our work in Loffler 2020, titled as Approximation Algorithms for Multi-Robot Patrol Scheduling with Min-Max Latency. I'm the Hao-Tsung as the presenter, and this work is co-authored with Peyman Afshani, Berg, Kevin Buchin, Jay Gao, Maarten Loffler, Amir, Nayyeri, Benjamin Raichel, Sarkar, and Haotian Wang. And in this talk, I'm gonna present the motivation first and mention the related work and challenge. And lastly, talk about our algorithm and proof. So the right figure is our scenario. You have, let's say, one or multiple agents, and you have several sites with some kind of weight, which is the green, orange dot here. And our output is an infinite horizontal schedule for all the robots. We define the latency is the maximum waited time duration between consecutive visits of that site. For example, for this agent, if he leave right now and come back within 10 minutes, then the latency will be 10 here. And depends on your schedule, this time will be varied. For example, maybe he come back in 10 minutes this time, 20 minutes in next time, then we consider latency as 20 minutes, the maximum value. Our objective is to minimize the latency among all sites. You can imagine it's like every site has a candle, and we want to light up the candle before the light disappears. And the latency will be like the size of the candles. So it will be like this. So you don't want the light disappear at all. And this objective functions has many applications. For example, in autonomous patrol, and like what we showed before, you can have a robot patrol the whole area and some important sites. You can talk about the warehouse robotics or retail, like you can resupply the items on the shelf. You also can talk about data collecting or charging mules in deleterial networking, like this one. And there are some related works. First of all, this objective function is not new. It has been talked about starting at 2009 and 2014. But their work only focus on single robot. And they have this log n or log Wmax by Wmin approximation factor. Wmax and Wmin is the weight among sites. And in 2016 and 2019, they talk about a dual problem. That is, minimize the number of robots with latency constraints, where the latency is defined as same as us. And they have this log alpha approximation, where alpha is a ratio of the maxima and the minima latency constraint. In the robotic community, they talk about empirical experiments on cyclic-based and partition-based solution. In a cyclic-based, if you have multiple agents, you first generate a tool among all the robots. And then you evenly put your robot on this tool, and then circulate. So it's like this. We have two robots, R1, R2 here. And the partition-based is to partition the area into many subregions. Each subregion will assign a robot for them. For example, this R1 is patrolled in these 5 sites, and this R2 is patrolled in these 5 sites. So in our work, we believe this is the first work for multi-robot scheduling with min-max latency. And we provide approximation algorithm either in general or special cases. Before we go to our contribution, I want to show you the challenge. The first challenge is that robot needs careful coordinations. And this is a very simple example. You can consider this is a 1D line, and we have 4 sides, S1, S2, S3, and S4. with weight 1, 4, 4, 1. And this is the distance, which is 3, 1, 3. Now, we show the optimal schedule for two robots. The robot 1 starts from S1, and the robot 2 starts from S3. So first, the robot 2 will do zigzag here because you can see S2 and S3 has very high weights. So he have to revisit and revisit these two sides. And because S4 must be visited sometime, so R1 will start move towards the middle. And when R2 see the R1 move towards the middle, R2 will start to move towards S4. When R2 go to the S4, R1 will start doing zigzag at the middle until R2 comes back. And then R1 can comes back to S1 and keep doing that. So this is just a very simple scenario, but it already shows the a complicated schedule such that robots need careful coordinations. And sometimes robots also need to have to stop and slow down. This will make making the schedule even harder. Now let's talk about our algorithms and proof. We provide 4 different solutions. In 1D, with uniform weights, means all the weights are the same, we have optimal solutions. 1D, but the non-uniform weights, we have 12 approximations. And in the general metric with uniform weights, we have constant approximation. General metric with non-uniform weights, we have this k² log W max by W min approximation, where k is the number of robots. Due to the time, I will only introduce the 4th one. And if you are very interested, you are very welcome to refer our paper, which already uploaded on the archive. So let's talk about the general metric setting. And let me show you the high-level idea of the algorithm. We first try to guess the latency L, and based on this L, we partition the size into K groups if possible. Each robot will be responsible for a group, and how they patrol on the group, we use the algorithm provided in elementary in 2009. It's a single robot with min-max weighted latency. Here is an example. Let's say we guess a latency L, and with this long, we already convert the time into a distance to be easy to understand. And let's say we have 3 robots in this example, and we have a bunch of sides here. Our second step is to map the weight of each side to the least dielectric value. So let's say right now the highest weight is 1, and we only have, let's say, the smallest weight is 1/4. So because they want to to map it to the dielectric value, so here we map it into 3 different groups. The black one is the highest weight from 1 to 1/2, and the blue one from 1/2 to 1/4, and this light blue one we have 1/4. For each group, we try to build an Amir max tree cover. And this tree length is beta L, where beta is 1 by its dielectric value. And your R cannot be too high. It have to be between 1 to K, from 1 to K. So here you can see for example, in the black group, we have 2 trees. In the blue, we have 3 trees. And this one, we only have 1 tree. Now the idea is to assign a robot to each tree or multiple trees. How we do that is we can see the B step first. So if there's no robot assigned to any tree, we first assign robot to one of them. And we start with the highest group, the group with highest weight. And we pick, for example, we put R1 assigned to this tree, and we set up just arbitrary site, for example, this one as a depot. and R2 to this tree. Because this tree is not close to R1, you can see L is very far away to a depot. Now, in the other case, if a tree is close to another assigned tree, then we assign this tree to this depot. For example, you can see here to here is less than L, so we assign this tree to this depot, and this one to this depot. And if that tree is too far away from this one, or this one, we give another robot. And this tree is close to this one, so we assign to this depot. So in the end of this algorithm, robot R1 will be responsible for these 5 nodes. Robot R2 will be responsible for these 1, 2, 3, 4, 5, 6, 7, 9 nodes. And the robot 3 will only cover these 2 nodes. This is a pseudocode of our algorithm. Okay. Now, the challenge now will be, what's the approximation factor? Can we bound it? And to bound this approximation factor, we need 2 lemma. The first lemma shows that this L, the generated latency from our algorithm is close to L, which means it's only at most k log W max by W min. And the lemma 2 shows that the L is not far from the optimal, which means the optimal latency L star must be larger than 2L by k. We combine these two and we have this approximation factor. The first lemma is not hard to see because if you remember in the previous relative work, I already told you, if you patrol an area with single robot with their method, they already give you a log W max by W min approximation factor. And you have k robots, so this is simple, just multiply with k, and you will show that your general latency must be less than this value. The second lemma is a bit hard, so I will put more explanation on this one. Okay, so let's look at this lemma again. So given L, if the algorithm returns false, then your L star must larger than this value. Remember, we have 2 cases to return false. The first one, you cannot have k min max tree with tree length less than beta L. And because this min max tree is actually a lower bound of L star, so you can easily infer that L star must be larger than L. The second case is more interesting. So let's say you can build this k min max tree for all groups, but there's at least one tree cannot connect to any other depots. And also the robots are also running out, means there's no free robot at all. In this case, we can have the following configuration. Let's say we have k robots here. We already assigned k depots, D1 to dk. We also have one more point as k plus 1, which from this tree. And remember, it cannot connect to any one of these depots. Now let's just look at this configuration and eliminate all the other nodes. We look at what the optimal solution would do here. So first of all, we only have k robots, but there are k plus 1 points. So there must be some robots visit more than one site. Now our idea is we want to modify the schedule such that every robot just stay in one point until the last robot will visit one of these 2. And what we do, we use the idea to speed up the robots. So here's an example. Say all the robots start with speed 1. Remember, this speed is not described in our problem formulation. We just assume every robot cannot speed up. But right now, we just a little bit misuse this and say your robot can speed up. This can help us to prove this idea. So For simplicity, we just assume all sides are weight 1. Now take a time t in the schedule. Say Ry is in some default di, and after that Ry will move forward and Rx will come to visit di. I'm sorry. Now what we do in the multiplication is we speed up this robot Rx such that it can take the job Ry need to do, and we make Ry stay in di forever. What we do is we speed up Rx at this time t until this moment when Rx sometime before t plus L when Rx in di in the original schedule. So by adding up the speed of Ry, we can make it in this way. So Rx will go here to here at the same time here, and Ry will stay on di. And if you have the next robot, come to di, you do the same thing. You speed up and pass by di and make Ry stay on di forever. So we call this multiplication as one round. And in each round, we can make a robot stay in the one side forever by this speed up at some interval. So after k rounds, there are k-1 robot stay in one side. And one thing I didn't mention that although we do this speeding up, but the sum of the speed among all robots in any time doesn't change, because when we speed up, we also make the other robot stay in the one side forever, which means its speed is 0. So with this way, the last robot, you won't speed up too fast. You actually speed up only at the most k. Now, for the latency of the last robot that he has to visit two sides will be at least 2L. Remember, we say because each side is far away, right? We cannot connect one of it, and they cannot connect each other too. So we have at least 2L and divide by k. And this is how we prove this lemma 2. And combined with lemma 2, we have this approximation vector. And just for your notice, like here I use a little bit different value in the paper, but they are both had correct proof. Okay, so here's a summary. We discussed the multi-robot min-max latency problem. We believe it is the first work to provide approximation algorithms. And the approximation vector we provide k-squared log W max by W min for general case. We also have other cases which I didn't introduce here, like 12 approximation, optimal algorithm for 1D. And we also have ongoing work to improve approximation ratio for the metric space with uniform weight. And here is the talk. I thank you for your patience. And if you have any question or if you are interested, you are very welcome to contact with me or others too. Thank you.